In this recording, I'm going to take you on a journey from initial ingest right the way through to some analytics output. I'm going to take CSV data in here, but the same principles of using RDF for ingest can apply to completely unstructured data as long as you have some way of identifying the field itself versus the value of any piece of data. In this, I'm also answering some of the questions that were raised during the live presentation of this during Dgraph Day in 2021. First things first, I'd like to introduce us, what we do, and how we do it. So I'm Mike Hawkes, and I'm the CTO at Capventis. Now, Capventis deal with all aspects of business data, and we help businesses get value from their data. And this starts in the most part from customer engagement, where we look at literally, how do you engage with a customer? How do you capture the right information at the right time? How do you communicate with them? And how do you interact with them? Through that and their journey, we then start looking at how we measure that. So we look at the experience and the management of that experience. We measure how people have been able to interact with a company, how those communications have worked, and whether or not people are satisfied with the service that they have received. We pass that through then into our analytics world. And in the analytics world, we're able then to create dashboards and other visualizations that allow us to see at a glance how the business is performing. And of course, we can pass that across to data science then to look towards predictive analytics and how to look at things to make sure that we have the right business resources available at the right time to improve business. Tying all of this stuff together, we have a data management and integration hub, and sat within that are a series of technologies. So, talking of technologies, I'll just very quickly skip through what our preferred partners here. So we have Zendesk from the ticketing side, and for managing support and support queries, we have Qualtrics to measure the performance of our team and how they work. And then we pass that through to the likes of our Qlik teams who can visualize information. Of course, we can also support the likes of Tableau and Power BI and so on. Qlik is just one of a plethora of visualization tools, but it's our preferred partner here. And within the data science world, we leverage the power of Dgraph here. And today, I'm also talking about our own integration tool, affectionately known as Glue. I'm the inventor of that. And this is all about bringing data together, managing it, and integrating systems in a way that allows us to pull information through Dgraph into all of these other landscapes, keeping data in place and being able to manage them as links rather than necessarily having to pull everything into one central data area. Now, in order to do that, I'll just very quickly go through our Glue product, what it is, how it works, and then I'll start showing you how we use things like ingest within the Glue environment. So our Glue platform starts off with a core. This sits on top of anything from underlying hardware, so we can have a bare metal implementation for microservice data collection, for example, through into the most common operating systems, so the likes of your Linuxes and your Windows desktops or server environments. We also support things like macOS and directly down onto small device platforms, the iOS, Android, even down to Pi and ARM technology stuff. We can run within Docker containers, and we can bring all of this together through the use of a series of scripts. So we have an engine that is capable of integrating and dealing with things at a network level and at a protocol level, and then sitting on top of that, we have the scripts that actually do the knitting between these lower level services. These individual services and scripts we've based around the Go programming language, so we've been very careful here to select a language that allows us to handle things like concurrency and synchronization. We want it to be extensible so that things that we do in scripting, if we find that we're doing it a lot or that we can improve the performance of, we'll move that into proper Go code. So our scripting environment is based on Google Go. So you'll see in a moment or two when I use it that you'll see things like the import, and you'll also see things around things that you're already familiar with as a Go programmer. We did originally have a JavaScript version of this, but we found that it was more difficult to get the language to handle things like concurrency and synchronization than it would be to flip into a native Go, or certainly a Go look and feel scripting environment. Sat around the scripts as well, we use Badger, And we also use Risterato in there so that we're having advanced caching, and we're having the ability to cache out to disk if we need to, or go across multiple core services running concurrently. One of our key things here as well is that we have to have this secured by design, and we make sure that we're able to have adaptable security models, so we can have security on one platform basically being augmented by security on another platform if that's what that particular customer needs. So onto the right hand side here, I've just lifted the covers here on the glue core, and you can see there's a load of stuff inside here that deals with how we manage the scripts, how we allow them to communicate between themselves, and also how we deal with things like exceptions, particularly when we're working in concurrent streams. Underneath all of this, of course, we've got our communications environment. So we have thread-safe memory handlers. We've got an abstracted file system that allows us to have something that looks like a file system, but is actually an API call behind the scenes. This is really useful for things like our embedded SFTP service, where you can have somebody coming in via SFTP, seeing a file that they want to go and collect, and that's actually making API calls across to the likes of your Qualtrics's or your Zendesks of this world. So in this workshop, we're going to start with some source data. In this particular case, as I said, we're looking at this from a CSV perspective, although this could be completely unstructured data as long as there's some way of differentiating the field name from the data value itself. So we've all had this. The source comes in, and it's a customer saying to us, here, have some data. We're not quite sure what it is, but this is what the business is telling us we can get. So from an initial point of view, we've got a list of schools here. This is publicly available data. And what I want to do is I want to ingest that straight into the Dgraph environment. So I don't want to sit down and define schema first, then try and work out a series of JSON structures in which to marshal the data and then input it. I just want to throw this thing straight into Dgraph. And it looks something like this. So firstly, this is inside our glue engine. I'm importing our standard products, and then I'm going to set a rate limit. I'll talk more about the rate limiter in a moment. So create myself a new Dgraph instance, and then within that, I'm going to run the ingest. So that just takes a second or two to run, which should be there. There we go. So what have we done? We've just taken a CSV file and we've ingested it straight into Dgraph via the glue engine here. Now, within this environment, actually we know that the CSV has got, as row 0 is the header. So we're able to extract the header, and then we're able to create the types based on the first row of real data. So we're able to define both the initial header and also the various types within that from a schema perspective. We're able then to pull together a series of RDF strings based on that data. Now, I mentioned that we had a rate limiter in there. The reason that we have a rate limiter is that I could convert this entire file in one hit. And I think this one's about 50,000, 60,000 records, something like that. So if I were to import all of those in a single hit, we'd end up with one transaction going across the wire to Dgraph. So obviously we now have the memory that's required for that. We've got the number of records that you're doing in a single transaction. And it means if anything goes wrong at any point through that, we've got to now unpick all of those in a single hit. So we can break these down into smaller lumps. So we're now dealing with two 25K chunks. Again, that's still probably too many. So we then ask the question, what is a sensible number of records, or do we want to do this through a sensible block size? Now, when I'm dealing with unstructured data, so completely unstructured data, I want to understand where each individual record has come from within every given file. This means then that the sensible block size, although may appear to be attractive, is actually going to potentially give us something that's very difficult to debug in the future. So I tend to go for the N records. In this case, I think I was breaking those down into 100 record chunks, lots and lots of transactions. And any of those can independently be retried or can fail. But as long as we keep the original source row, we know then that we are in a position that we can find the problem and we can resolve it, but we've got a small number of records to deal with. So the rate limiter in this particular case is a really, really simple thing. We're not putting any time constraints around it. It's basically just a channel of a set size. And I had a couple of commands there within the glue environment where we were saying set a rate limiter of, in that particular case, 50, and that's the number of concurrent transactions that we're running. And again, it's an arbitrary value. Then we have the queries themselves, and you can see that for any query or mutation, we can just put this really simple wrapper around the outside of it. Now, I will say at this point that any of the code we show you is stripped out a little bit, and I'm not putting all the error handling in there, and I'm not putting things like context control and other things that you'd expect to see in production code. This is simply so that we can talk through the principles of the code without necessarily having to have anything at a low level. It will work, he said, famous last words. So as far as I'm concerned, this is running code. It's just with some of the error handling taken out of it. So what we see then in the query itself in this case is every time we query it, we simply push something else onto that particular channel. If the channel's full, it's going to sit there and wait. And as soon as there's something that a slot becomes available, it will then take it. And we've got the defer there to say at the end of it, just pop that back off that channel. And again, that will give us a rate limiter based on how fast Dgraph can manage each of these individual transactions. So here we have fixed record size block that's being controlled by the code elsewhere. Each one of those is being fed through in its own little Go routine, and then we're having the limiter here controlling how many we're passing through to Dgraph at any given time. Now again, in the real models, we also determine which of the glue engines should be feeding that into Dgraph, because we could have several of these running in parallel. So having got that in place, I want to talk through the ingest process itself. I mentioned before that the header is in row 0. And there are a few design constraints here that I'd like to do. First of all, I don't want to take multiple passes through the data. So how do we do this on a single pass through? Well, I'd like to create a schema on the fly as I go, and I'd like to create all the individual types on the fly as well. So I can literally, as you saw in the original code there, literally just fly through this by saying ingest a given CSV. We're there, it's done. In this particular model, I'll use CSV Reader. There are others, but this is as good as any for demonstration purposes. And I'll also show how we use strings builders. Now this can help with performance because we're not then appending to a slice all the time, and this makes things considerably quicker. I'm going to just very briefly outline how we deal with dirty names and dirty data, and also consider how things like rows and types exist within the existing Dgraph piece in case I'm appending to an existing model rather than anything else. So what I'm going to end up doing through this is creating an object type that will go into the schema, and I'm also going to create all the individual edge definitions. Again, that will go through to the schema, and we can do that as we go through. The one thing that I do create for each one of these is a row counter, so that's the only thing I'm actually generating here as our own internal field. And that's simply so, as I mentioned before, if we do have a problem during ingest, or we've got a problem with a particular piece of data further on in something else that we do, then I can go back to the original data source and say, oh, it was row 34 on that file that gave me that problem. Now the other thing that I do here is I want just to mention that when I ingest something, I will take, for example, the schools ingest there, and that particular one, I would have then whatever the name was with an underscore followed by all of the edges. This means now that I would have schools as a type, then schools row, schools name, schools town, whatever else that may be. So the schools underscore gives me a way of always being able to put this back to the original source should I need to, but it also makes sure that if I've got two different objects coming in from two different data files with the same heading name in the CSVs, for example, that they're not going to collide, and I'm not going to end up overwriting name with name from a different source. So the code looks something like this, and again, we stripped out a lot of the error handling, but this would be functional code if you were to try it. So on the ingest itself, we're doing a few things. First of all, because this is going to be running within a scripting environment, I want to know when things have finished. So I want to wait as an overall function until this is finished, and that way I'm not then starting to kick off processes against the data, not knowing whether all of the data has been ingested. So simple wait group there to control this particular process. We then open the file, we go in and we create ourselves a new reader based on that file. Then I'm going to create the various variables that I'm using here. We've got a row counter, we've got the header as a slice of strings, and then we've got a couple of strings builders here, one for the schema and one for the schema types. Because I've now got a builder that's available for the schema types, I'll just write out the header there, which is basically saying type. In the one that I've just done, that would be schools as the object name, and then the opening bracket there for the start of the definition. So that's been written to the schema type. And then I've got another strings builder here, which is for the RDF code. So this is the code that's actually going to hold the records themselves and the definitions for the various edges and values. Then we kick off into the main loop here. So we're going to read something from the CSV file. If it's the end of file, then we stop at that point. We've done everything we need to do. For simplicity, I'm just going to say that if this is the first row that we're coming across, then this is the header row. So what I'll do at that point then is write out that we need to have a row for this particular edge type, or for the type of record. So write out the definition there for that. And I'm also going to write out the type definition within the schema itself for that. Then for each one of the headers, we just append those as types. Now, nominally, I'm just showing for the sake of how we do it, replacing things like spaces or open bracket or close bracket, or things that would cause the schema to throw an exception if we were to try to insert that into Dgraph. Again, in the real world, we'd do that through a regex and we'd have this handled properly. But for the sake of a demo, that works. And then we append those to the headers. So we've now got a slice of headers, which we're going to use in a moment or two. We write out the strings there, which are containing the type definitions and are also then finishing off the overall schema itself. What I then do is I write out to the schema onto Dgraph both of those things that we've just created. So here's a list of all the fields, and here are the types of those fields. Now we get into what the whole loop is doing. So I've just collapsed that section down, which was controlling the schema. So this is the full for loop for doing an ingest based on a CSV file. So what are we doing? Check to see whether we're end of file. We've just seen that. If it is, we stop at that point. We then read the header rows and process those. We've just done that, and we've created the schema entries for those. Again, if I'm dealing with unstructured data, I can hold on writing the schema until after I've done the processing. So I can actually process all the records, inject them into Dgraph, and then write the type definition out at the end of it. So we can deal with either structured, semi-structured, or unstructured, as long as we know the field types there. And again, we can make assumptions about field types. So if we're not sure, do it as a string, because that then will work. And again, we can also deal with that as escaped strings, so that we end up with binary data effectively being put in to Dgraph as part and parcel of an ingest process. So for each one of those rows, we simply then create a string which looks very, very much like the one on the left-hand side, where I've got the underscore colon, then a row number. And because I'm ingesting schools data here, schools name. So the schools was the object name, the underscore is something I'm creating, and then the name is actually the header name. So we have from the CSV file header name, and I've inserted into this underscore one schools underscore name, and then the value of it, and then the full stop. Now that's as much as I need to do for every entity that I'm putting in place. So the underscore colon one is a Dgraph specific thing that says you can create a new a new node, and then attach this edge to it. Everything that has that underscore colon one will be attached to the same node. So that allows us then to have multiple edges coming off that node, And again, I haven't had to predefine any of this because I'm generating it on the fly. So what you'll see here then is, as a modulo check, I'm saying let's now go for whatever the block size is. So say if our current row number modulo, for argument's sake, 100 equals 0, then we've hit the 100th record. Let's write that string out through a Go routine all itself. So dump that out, work on the next row, and just keep going and keep going. So that's the bit that's now controlling how many records we're getting pushed out per transaction. Because it's in its own Go routine, remembering that section that we did before, this is now saying if the rate limiter has capacity, then that's fine. If not, then that Go routine will effectively be put on hold until such time as the Go routine channel is available to Dgraph. So that runs a mutation. And again, I'm just got a really simple error handle here, just saying if there is an error, then print out that and carry on. In the real world, we'd actually cancel the context at this point and stop the ingest. Once I've added that particular block of records, I can now reset the RDF and move on to the next row. So all we're doing here is creating a series of RDF strings. They're very small and they're very, very flexible in terms of the structure. So if I'm importing something, for example, as a JSON structure here, similar sort of process, but it doesn't matter then whether we've got all of the fields on every single JSON record that's come in. So if I didn't have certain fields inside the JSON record, it wouldn't matter because the RDF wouldn't get generated for it. And again, typically in a JSON environment, I would read through and ingest the data, push it across into Dgraph, and then at the end of that, write out the type definitions back into the Dgraph schema. So that allows me to have that variable input and allows me, if I wanted to handle unstructured data in that kind of way. Now that we've imported all of those, we may well have the last few records that have been left, if it's not a regular block of 100, so the trailing 23 or whatever we now write out in the final chunk. And then we had that wait group set up right at the very beginning to say, can I wait until such time as everything's finished? That's the wait group end there. Just to show you now what's happened inside Dgraph, you'll see, if I move that over onto the types, you'll see now that I've created a schools type. So the ingest command was ingest schools.csv. We've stripped off the .csv. We've created schools as a type within schools. We've had all of the various edges that have been defined on the fly. These are now associated with with that schools type, so that we now have everything that we need there to handle that particular piece of ingest. If I run a command here to say let's go and get one of those schools, you can see that I have now returned the schools, and all I've done here is an expand all, and that expand all also proves that the type system has worked there. Interesting to note here that I've said go for the 3000th record, and yet if you look at schools __ row, you'll see that's at 1417. So that is demonstrating that this is working in a concurrent model. So we've ended up with different parts of this being written faster than others. And again, that just sort of underlines why the row is important. So if I was looking at that at row 3000, because there'd been a problem with that particular record at some later process, I wouldn't know necessarily where that had come from. Whereas here, I know where it came from the original source. So we've taken some source data and we have now ingested it. We've also created a schema on the fly. Now what I want to do is I want to link some of this data together, and this is something where the graph world absolutely excels. We want to be able to have multiple links between different disparate data sets, and in order to do that, I'm going to bring in another data set here, which is simply a list of towns in a CSV format. So we'll do the ingest for that. So if I ingest the town list, there you go, it's really quick, that one. And now I'll talk about what I'm actually going to do. So town list was the name of the file, so I end up with town list _ whatever. You can see my row counter there. And you can also see that there is a town list _ town, which is the string, and that will allow me then to link to the schools _ town within the original schools list. Now what I want to do with that then is again use RDF to do this. RDF gives me the ability here to link all of these various data sets simply by defining those two entities. I don't need to worry about the rest of the structures here. The only thing that will make a massive difference here is indexing. Now, typically I would say do your ingest and then index. And that process means then that we've got the fastest possible ingest, then we've got the indexing process. This allows us, if we need to tweak the indexes in order to work in a particular way, whether that's full text or whether it's exact. For linking generally, I would also say make these exact index pieces. So let's now go in and we'll index. So there's my indexing piece. That takes a second or two to run. And now I'll do the link itself. So if I walk you through, linking is actually perhaps a little bit more complex than you might think on the face of it. So the linking process requires in all 6 objects. So why 6 objects? Well, we've got a source type and we've got a destination type. So we have a schools and we have a town list. We've got the field that we're coming from, the schools town, and the fields that we're going to match in the other source and destination data set. So we have schools town and the towns list town, source and destination. And then I want to have an edge which is pointing from schools to town list, and I want to have an edge which is going from town list back to schools. So that's the reverse edge. Now Dgraph does have a reverse edge capability. I tend to stick with being explicit in the links, however, for the reverse edge, because that way it's absolutely clear when I'm running any query that I'm following, for example, a town list to a school's reverse edge. This means now that I'm not getting lost in the reverse predicates here. I actually know what the end is and I know what I'm expecting at the other end. So it's all well and good doing the reverse edges. I just find that when you come back to queries in 6 months or in 12 months time, you quite often find that reverse edge means that you then have to start scrabbling your way back to the schema to work out what exactly that's pointing to. By doing it explicitly like this, I end up just looking straight at the query and understanding that that's going back from the town list to the schools. Then I'll have my schools types within that. So let's look at what I do. First things first, I want to go and fetch the schema. And what I'm going to do is I'm going to modify the schema to have these new forward and reverse edges inside them. But I want to make sure first that both the edges, schools town and the town list town, exist. So let's go and get the type for that particular schema type. So that will give me schools type from the source. Within that, I'm just going to check whether the predicate exists or not. So I'm looking in this particular case within schools for schools town. Now, assuming that exists, that all's well there. If it doesn't exist, actually I've got nothing to link on, so that becomes an error at that point, so I stop the process. I don't actually need any more information, simply a binary, does it exist or not? And we do exactly the same thing there with the destination. So does the type exist? So have we got town list, and does the field town list town exist within it? Yeah, it does. So we're okay, carry on. Back to my favorite strings builder here. And you'll see at this point what we're now going to do within the schools source type is I want to make sure there is a schools town list edge. So this is my forward pointing edge. So what I'm doing within that then is just saying, write out the type to the strings builder. Within that, add in that schools town list edge. We then rattle through all of the others, adding all of the types in there. If that edge already exists, fine, ignore it. But if not, then it's been inserted. So what I can guarantee coming out of that for loop is that the schools type will have a schools town and a schools town list at minimum, along with the rest of the type then that's been inserted. So I then write both of those pieces out to the schema. You'll notice at this point as well, at the end of that the forward predicate I am saying is of type a list of UIDs. So that can be more than one going in the forward direction. Again, we have the opportunity here to say I would prefer this to be a one-to-one or a one-to-many or a many-to-one. It's up to you how you construct these, but for the sake of this demo, I'm saying that, but the whole thing here will be a many-to-many relationship. So that square brackets around the UID in that last write string is saying, write me the forward predicate and tell the schema that this is a list of UIDs. In other words, a list of forward predicates. I want to do exactly the same thing now for the destination. So this is the other part of the schema now. So we're saying within the destination, make sure that we have a town lists town and that the town list schools is in there. And any other parts of that type can also be in there at that time. And again, final line there is saying that this is a slice of UIDs. Therefore, again, we've got that piece specifically to say this is many-to-many. Okay, so now let's run a query. And we typically run queries in a very consistent way. We have, in this particular instance, I'm running this purely as a string. I'd normally run this with a string with a set of variables associated with it. But the principle is really straightforward. We run the query and then we unmarshal the result. And that's basically what we do for everything with Dgraph, whether it's mutation or a query. The queries themselves, in this particular case, are this, and as I say, normally I do it with a variable declaration block at the end rather than having just a string insert. But for brevity and for demonstration, we'll just do it this way. So you can see that we have our source query there saying, go and find me a particular type. So in this case, it would be run me a query of pulling back all of the nodes that are of type schools and return to me all of the UIDs, so here are the record numbers associated with those entities, and also bring back a link field for that. So this is the value of schools town in this particular case. Now, I'm using a quirk of or a feature of GraphQL here, in that I'm renaming the field on the way back out. Now, this allows me to keep this as a completely generic query, and this is a really nice feature of GraphQL. What I can do here is I know that I'm actually pulling back, in this particular instance, the school's town edge, and I'm renaming that to link field in the structure. So I'm pulling back the UID and the link field value in this particular query and pushing those straight back into just a slice. Destination query is similar. We're now saying, in this particular case, the final query on that page is saying go to the type town list, and we're going to filter it based on town list town being equal to whatever the town is in the first query. Now, this means then that if I'm searching for a town, say the first query returns a UID of 1 and the link field is a town called Crew, I would have a UID and Crew. In the second query, I'm now saying find me anything of type list town, of type town list, and within the filter we're then saying where within town list we have town list town equaling Crew. So that would just return the UID at that point, and that now means that I've got a list of UIDs that apply in both directions, and I'll be able to create a list, many-to-many list, by just taking those two UIDs and putting them together. So what does that look like? Well, what we have, again, within this particular range, I'm doing it. The first time I hit it, I'm writing out the schema. And then beyond that, I'm now starting to push everything together so that we have the structure for the return data. I'm now going to run the query to go and find all of the towns that link, and then I'm going to unmarshal that data back into a slice. Finally, I build a set of strings that are actually the UIDs themselves. So you'll see the final part of that is saying write out to the string source UID, the forward predicate, the destination UID, and then I write back destination UID, the reverse predicate, and the source UID. That's actually writing the link backwards and forwards. So what that actually generates is something along these lines. We're seeing that the source has schools town list to another node. That other node, then I'm inserting a town list schools coming back the other way, back to the first node again. And we're doing the same thing here, saying that we're making the assumption that nodes 5 and 6 are actually both pointing to the same town. So that's how the RDF strings work. But that's actually all I need to write out to Dgraph in order to get that to link. So we've now taken some source data, we've done the schema management around it, we've linked them, and we've linked that again through RDF and through tweaking the schema. The final stage of that then is to actually show all of this working. So if I show that, and then I'll hop into Dgraph itself and just prove that those links have been made. So let's just put this in. So you can see all 6 of them there. And if I OK that, so quite quickly there, and then what we'll do with that is we'll flip over to Ratel and show that. So there's the query, and you can see that I've got a list of schools that have all been linked in that particular case from Crewe. There's one for Congleton, and if I just do a graph of that, I've just pulled back the first 3 of those that have been linked. But you can see that they've all been linked properly. So there we have it. We've done the links. Now then, grouping is the next part of this. I want to be able to pull everything together into a series of groups. Now this isn't a natural graph thing in some ways. So group in a graph world is really just a process here of allowing me to do something along the lines of select distinct if I was looking at it from a SQL world. I want to have a group of things which are effectively based out of one type that have multiple nodes linking out of it. So similar to a link, but I want to create these on the fly. And it looks a little bit like this. So same 6 things, but in this particular case, we're going to create a new type called towns with town names and town schools in. So that will run, it'll take it a fraction of a second longer to run. But that's now creating those groupings for me. So it's effectively a series of links again, but in this particular case, we're saying link the schools to a new entity called towns, and away we go. So if I actually walk you through this, we have schools as our original type. In that, I want to create a group around the school's town. So everywhere where we have the same group town, I want to create a forward edge to call schools to towns, and then create me a completely new type that contains towns, the town's name, and a reverse edge from that back to the school. So similar sort of process. We've got the same 6 objects that we would have in a link, but this is now creating your forward and reverse edges. It's also creating a new type called towns. So when I look at that in the schema, you can see now that I have created towns with a town name and the town's schools reverse link back up. So this gives me this query where I'm saying, give me everything of type towns. I'm just going to filter them, so we've just got the first couple of them. We knew that Crewe and Congleton were there from the quick scan that I did earlier on. And we're going to return the town's name, hop along the edge there to town schools. So we're going to go to a schools node. For those, we're going to pull back the name of the schools, and then I'm going to hop along the schools town list edge to give me the town list town name. So we should end up with the same name in theory as we had from the start off. So let's just have a play with that and check that does what it should. So there's our query. We can see now, yep, we've got two sets of links in there. So everything's working there. Might just simplify the JSON out while I'm here to make it slightly cleaner. So what we've got at the moment is town's name is Crewe, which what I asked for. Then we've gone down the edge there for the town schools edge to school's name. Then I've followed the town's list edge down to give me the name there. So as I predicted, town's name and town list name both end up being Crewe, which is okay there. Oh, nope. We'll just go back and correct that. There we go. So if I run that, we can now see that we've had the grouping and we've got the right names coming through from that. Typically, of course, if I do that kind of thing, I would remove the predicates that I no longer require. So we've now ingested data, we've handled schema, we've handled linking of data across edges, we've also grouped edges together, and to a certain extent here we've now created a series of very dynamic graphs from this. So I'm able now to say that I had no idea when I was first starting that I had a load of information on schools, and I had another one that was the towns list, but now that I've been able to link those and start seeing how they interact together, I'm able now to start pulling information together. So from an integration standpoint and from a general data management perspective, that becomes quite useful. Now, what we then do within the Glue engine is I want to pass this out and make it available to remote clients. If we think about the likes of conventional REST APIs, we have here something that is really easy to work out from a group and a routing perspective. So typically, a remote client will come in, make an HTTPS request, and what we have then is a set of routing directives in effect. So index.html might be a piece of local content. We might have handlers, for example, to deal specifically with content. We might be passing this through to an API where, for argument's sake, client pull back ID number 1 from our client's database. Or alternatively, we can run through with the sort of things where we have query strings, or we can pass it through within the body of the request itself. So that's all well and good. We've got lots of different ways here of understanding the routing and understanding the way that the various requests will operate, and we're able to control that quite nicely. We're also able to pass errors back at that sort of granular level. So something happens within my client's API, so that particular ID doesn't exist, I can pass back something that says, nope, sorry, that client doesn't exist. A proper error. Now, each one of those has an individual handler out to the back end as well. So we're able then to be able to process this directly through the routing. Now, within a GraphQL client, unfortunately, it becomes a little less obvious, because what we have here are just two endpoints. We have the GraphQL endpoint itself, and we have a GraphIQL for those that support introspection. So within these two endpoints, I have no way of knowing where the error occurred, if an error did occur, other than say something has gone wrong. And typically that means then that within our middleware layer here, we have to start providing some kind of abstract syntax table or similar, so that we can work out what it is that's happening, work out what the nature of the request is, and we end up with our own resolvers here. And this then says that we, in effect, need a federation layer. There are lots of different names for this, but I think the industry is standardizing slowly on federation. So we have an incoming request. We then have something which is mixing and matching the various requests across dynamic graphs, whether or not we need to stitch together multiple schemas. So some of it's coming straight from Dgraph, some of it's coming from our internal stuff, some of it's coming from an API, which is a resolver wrapped around a REST call, for example. We also need to be able to manage error handling, but manage that in a sensible way. So it may be that I'm allowed to gain access to particular fields, but perhaps not others. Now, does that mean that the entire transaction fails, or does it mean that I should be passing back only that I can see? So the context management piece here is really important, as is security. So all of this stuff needs stitching together, and again within our Glue engine we do this federation piece. There are external providers that can look at things along the Apollo Federation world, and I know that Dgraph itself is moving into the Apollo Federation world as well. But this allows us to control things at a much more granular level. And it also means that from an integration perspective, it's not simply saying that we're going to connect an API to an API, or we're going to just go and suck data in from external systems. We're actually saying here we can do this intelligently, and we can resolve right the way down to an individual field level with the right security model and context wrapped around that. So if I show you now what that looks like when we're running an external client, in this particular one, I'm extending a query out. We want to pass a query that is available for our Qlik data tools or data analytics tools to be able to visualize. And what we're seeing here then is a standard GraphQL query in Insomnia. So I've given it a set of parameters there to start and end date, and I'm then saying, give me a list of the following fields. Now in this particular case, project is coming from a Rike system. We have the other fields within that particular one. Task is coming from, again, within Rike. The staff is coming from 0, whether it's been invoiced or not is coming from 0. And then we have things like the time entry ID and the others coming from our various project management systems. And Dgraph is putting all of this together. It's providing the link between the data, and I can keep all of this data into their individual systems. So what we now have is a front-end client which is accessing a federated graph query through our glue layer here. And for those that are coming in from things like Rike or Xero, we're actually doing a GraphQL wrapper around the REST APIs that those systems provide. And we're also handling things like rate limiters to those platforms, and we're also handling errors and exceptions across those, including things like network retries and these sorts of things. So that then looks like this when we start pulling it back into the front end. So what we have here is a whole sequence of events, of types. So this is that same data, and I'm now saying that this is available through our analytics platform. We can look, for example, for this lawyer's service, where most of the business is coming from. It's coming from their healthcare service. I can do the things like the force diagrams that you see within Dgraph, but I can also start to pull together more conventional data analytics based on the information that's coming through. Now, as I'm just flying through these, it's interesting to note that we have the choice of where we would like to put this data. So do we want some of it coming in from the likes of Dgraph, or do we want to have it coming from the analytics tool? Now we have the ability with Dgraph to run some really advanced queries, and it makes sense to run those within Dgraph and return to your analytics tools only the information that's been selected at the time. And so there's an integration piece at the front end here that says that we need to work with these services to allow them, or within the analytics tools, to allow them to access the information that they want on a live query basis. And that makes it incredibly flexible. We're able to use Dgraph and the power of Dgraph to handle the low-level queries, and then we're able to use the analytics tools to pull that data together to be able to visualize it and to put it in place. And we don't necessarily have to pull all of the data off all of the platforms in order to allow the analytics tools to do things like this. For example, I'm just going to select a particular area of the business. Now, for those where I'm actually wanting to create dashboards and I'm wanting to create things that are available in a pseudo real-time basis, that means that the ETL process that you'd normally see in data visualization has been vastly simplified. And for that reason, I really like the ability here to just use Dgraph to query the data, the likes of Qlik to be able to present and to visualize it, and to allow me to access it in a way that's useful for the business and that the business can consume. And this is significantly easier in the Dgraph world than it would be in a conventional SQL world. So just finish off on the visualizations. So what we are now seeing then is the analytics output. We've gone from the source data, which was partially structured in that it was a CSV file, but that could have been completely unstructured as long as we had a field type with a value. We've gone through the ingest, we've gone through schema management, creating the schemas on the fly, we've linked them, we've grouped them, we've gone through this process of creating a federated dynamic graph, so that data becomes available simply by following the ingest process. It makes itself available to the federated layer, including things like introspection, and then we're able to pass that straight out to the analytics tools in order to present them and to give you visualizations. Anyway, that's the life cycle here. I hope you find that useful. If you've got any queries, or if you want to reach out to us, please feel free to do so at Mike Hawkes, or alternatively you can send me mike.hawkes@capventis.com. Just out of interest, we're hiring at the moment, so if this type of thing interests you, we'd love to hear from you if you want to work in this environment. Anyway, that's about it. if, as I say, if you have any queries or if you'd like to reach out, please feel free to do so. And thanks for taking the time to view this today.